Okay. Hi guys. Wow, we're down to three students. Okay. All right. That's okay. We'll continue. What I want to do is I want to go to Canvas. We, we can look at the calendar just to make sure that everybody is on the right track and nobody is being surprised with anything toward the end. And so today is the 24th, okay? Thursday and Friday. Obviously, Thursday we won't have class. We have Thanksgiving coming up. And then we will finish chapter 14 today, very short chapter, the rest of it, that is. And then next week, which is the first, we'll do the final chapter, which is even shorter. Okay, so you're going to have a lot of quote study days here left over because after the following week, December, let me make sure. We're going to December here. The 8th, we have exam number 5, which covers chapters 13 through 15. So we should be done with all the chapters, those chapters for sure, and get you ready for that. You got homework coming up. Then the following week, which is on the 15th, is the final exam. Okay, so that covers chapters 1 through 15 as comprehensive. I do have an extra credit running. It's in the section with the final exam. It's called the density extra credit. If you are going to do that, you have until the 18th. I may have to move that over to the 17th because I got to get the grades in. I think they shorten the time now. I may have to get them in earlier, but as it stands right now, the extra credit is due on the 18th. They may shift to the 16th. What the extra credit is it's a file. Download the file, print it out. Keep well, you don't have to print it out. What am I saying? It's a Word document. So keep it open so you can input your data into it. And in that file, there's a link that sends you to a simulation that deals with density. And so you'll be taking blocks and calculating the density of these blocks. Do note when you immerse those blocks, basically they tell you grab a block and immerse it into a liquid. Immerse it completely because you want the total displaced fluid coming from that block. And the blocks would be either constant weight or constant dimension, so it's going to vary. So you can calculate the density. The other aspect about the extra density is, think about this for a moment. They show you 100 milliliters of a liquid to make a difference what liquid is. It's a liquid. You immerse the block, and then you get a new volume reading, which could be, let's say, 120. Okay? Remember, the 120 is not the volume which that block immersed. It is the difference between the volume of where it ended, 120, minus the volume that started, which is 100. So that block displaced 20 mils, not 120. Okay. So remember that aspect of it. So yeah, so you're going to do extra credit. Basically, when you're done with the file, you save it. There's name instructions on how to save it with your name and so forth. Go back into the assignment, upload the file, and then I will grade it once it gets uploaded. Right now, it stands, I believe, at 15 points with respect to extra credit, and it's applied toward the final exam section. Okay. All right. So that's where we're at. Any questions about all that? I don't want you to be surprised. So basically, on the 17th, if you look at that, because the final exam's the 15th, that's the end of class. As far as the 15th, and that will be open. It's the same time span that we have done in the past with the other exams. So 7 to 11:59. plan accordingly, because I know you have other classes too, and do plan accordingly. Okay.
Do you know how many questions are on the final and the time limit?
The time limit, good question. I don't know how many right now. It's in the process of being created. I will find out, and next time we'll meet, I will forward that information to everybody. But it would be, it's a good question. I know it's the way they got it worked at 60 points total. I don't know why, for some reason, they got it at 60. And in the past, it's been about maybe 30 questions. So, but I don't know for this one specifically. I do know that on the website, there are some old final exams you can use as a reference, and that could give you an idea of how many questions. Okay. But once I know more specific information, I'll pass it forward. All right. Be aware we have a multiple study days. So I will be here. Doesn't mean that I won't be here. I will be here. So if you have questions, do come. This is a good spot to bring your questions through the study date. Now, not only do I have this, you have the same schedule for my 1 o'clock class, it's the same schedule for the 4:15. So if that doesn't work for you time-wise, 1 through 2:15, then you're more than welcome to come to my 4:15 at 4:15 to 5:30 class. And then another additional, I have my SEC class on Fridays from 1 to 3. You're more than welcome to drop by with that too, because they are roughly one chapter behind time-wise. We only meet once a week, so they're one chapter behind. But that's another resource if you want to listen to whatever, that topic again. Okay. Any questions? All right. Well, let me start up with where we ended up on slide 20, according to my slides. Okay, we were talking about IMF, and those are intermolecular forces. These are forces that deal with the interaction of molecules amongst themselves, okay, as compared to intra, INTRA, which basically deal with the bonds within the molecule. So the intermolecular forces are dependent on polarity of the molecule. So here we go. We dealt with polarity and first figuring out the formula, from the formula, figuring out the structure using the shapes table, and then looking at the bond, polar bonds, and then determining whether a molecule is polar. So it's all coming together here. And so intermolecular forces, we're dealing with covalent compounds, okay? Covalent compounds, either polar or nonpolar. Now, with respect to nonpolar covalent compounds, and those are compounds that either have all nonpolar bonds, like a diatomic, all the diatomics, or carbon-hydrogen bond, or they're compounds that had polar bonds, but the position of the polar bonds are such that they cancel each other out, like carbon dioxide. Carbon dioxide has polar bonds, but those two polar bonds cancel each other out, hence the molecule is nonpolar. So any nonpolar molecule, the only force they got to deal with is London forces. Okay, plain and simple. That's it. You don't have to worry about anything else. Now, when it comes to the other three forces, dipole-dipole interaction, hydrogen bridging interaction, and ion dipole, those deal with polar molecules. Now, the ion dipole molecule, the reason we put it there is because the ion obviously is a ionic compound. Okay, so a metal, non-metal. But the dipole interaction is aqueous, which is a polar water molecule. So hence we have to deal with ion dipole interaction. And so if you're looking at the problem and they're talking about an ion in the presence of water, then the only interaction involved there with respect to IMF is the ion dipole force. Okay. Now, with respect to dipole-dipole interactions, every ionic excuse me, let me restate that. Every polar covalent compound, okay, has a dipole-dipole interaction. That's why it's polar. Okay, let me repeat that. That's important. Every polar covalent compound has a dipole-dipole interaction. The electronegativity of one of the elements is much greater than the other, hence we have a dipole. Okay. Now, where they differ is only a select few, in that those polar covalent compounds that have hydrogen bonded to nitrogen, oxygen, or fluorine, in this case fluoride, then those three elements bonded to hydrogen have what are called hydrogen bridging, which is much stronger than the dipole-dipole interaction. Okay? Yes, the hydrogen-nitrogen is a dipole-dipole bond. Okay, understood. We understand that. However, in those three examples, they have an additional force, which is called hydrogen bridging force, and much stronger than the dipole-dipole interaction. Okay. So NOF, not on file. One way to remember it: nitrogen, oxygen, and fluoride, and hydrogen bonded to those three elements give you hydrogen bridging, which may also be called hydrogen bonding. But that's the old naming of that. I'm trying to get away from that because it's not truly a bond. It's an interaction. Okay, so that flow chart kind of helps you determine where you need to be. Okay. Now, why do we need to know that? Because this helps us determine properties of these compounds. These properties, and we're only going to deal with 4 of them, are directly related to the IMF interactions of the molecules. Okay. Something what is called vapor pressure. You're familiar with that. You got a soda pop container, shake it up, you build the pressure up right in that gap, that space. If you were to open it up, you're going to hear that. Okay. There's gas molecules between in that open space in the container and the liquid. If we had a pressure gauge and we put it in that empty area, what looks empty, it would have a pressure, air pressure. We call that vapor pressure. Okay. And again, the IMF interactions determine the strength of that vapor pressure. Boiling point, that is the temperature at 1 atmosphere by which the liquid goes into the gas phase. For water, it's 100 degrees. Another example is ethanol at what, 78 degrees. Okay, so intermolecular forces have a big factor on the boiling point. Surface tension, you're familiar with this also. You just clean your car, you got it nice and waxed before the car is dirty, right? And if you spill water on it, that water kind of spreads out. But then after you clean it up and then you wax it, give it a wax job, it's nice and shiny, and you pour water, what happens to that water? It beads up. It has to do with the surface tension, okay? Both the liquid and the surface, but surface tension, and that's how much the water beads up, is dependent, how much the liquid, I should say, beads up, is dependent, again, on IMF interactions, intermolecular forces, as viscosity. You know, the example I used earlier was honey and water, honey being very thick, water not as thick. In other words, viscosity of honey was much greater. That's because the IMF interactions of the honey molecules was much stronger. They hold on to the molecules greater, causing it to flow much less, or as far as speed is concerned, it won't flow as readily. But what happens when we heat up the honey? The flow increases, and what we're doing by adding energy into the system is we're breaking up the IMF interactions. We're breaking up those forces between the molecules and allowing honey to flow a little bit smoother. Okay. All right. where we at? So we're going to be looking at those 4 particular interactions. Okay. I mentioned vapor pressure. Okay. Vapor pressure is just liquid in a closed container, and some of that liquid is going into the gas phase. We all know that we open up a soda drink in a bottle, we hear that is a carbon dioxide that's in the gas phase. Okay. Now, liquids do the same thing. Now, in that case with the soda pop, it's an extreme example because I got carbon dioxide dissolved in water. But the same thing happens with liquids that by themselves. If I were to take acetone, close it up, and do the same thing, it would also do that sound because acetone has a very high vapor pressure because the IMF interactions are much less, whereas water, not so much. Okay. Obviously, what happens if we were to take any liquid and just leave it sit out there, it will eventually evaporate. Remember that these molecules of liquid are bouncing against each other. And some of them being on the surface are being hit by other molecules, and that allows the transfer of energy from the moving molecule to the molecule on the surface to actually kick it into the gas phase. Because that explains why we can take a cup of water and leave it on your kitchen top and come back in a couple of days, and guess what? The water is evaporating. Well, how do you do that? Normally you heat it up, right? You add energy to it and you can evaporate it. But a cup sitting there all by itself, it evaporated. Well, again, that's because a couple of things. The intermolecular forces, if they're not very strong, some of that liquid is going to go into the gas phase with time because the liquid molecules are interacting with each other, and eventually some that are on the surface get kicked out and go into the gas phase. All liquids will eventually evaporate. Okay, now that same thing, if we put a lid on it, those liquids, some of them go into the gas phase, and if it's closed, we build up pressure. Okay, and that is the vapor pressure. So if we have strong IMF interactions, our vapor pressure will be lower. Now think about that for a second. If we have strong IMF interactions, that means that the molecules in the liquid are being held on to each other strongly, such that very few of those molecules are allowed to escape into the vapor phase. Okay, because going into the vapor phase, that's where the vapor pressure comes into play. So if the IMF interactions are strong, less of the liquid goes into the vapor phase, therefore the vapor pressure decreases. Okay, and the converse is true. Weak IMF interactions causes the vapor pressure to go up. Okay, this diagram here says which has a weaker IMF. Well, we look and analyze the gas molecules that are depicted in the gas phase, and those are the ones in the spheres that are just all over, separated. You can see here the ones that are somewhat organized, there's liquid phase. Okay, so they're in the liquid phase. So the one on the left has a lot more gas molecules, vapor molecules, I should say. Okay, that would suggest that A has the weaker IMF interactions, which means that A would have the higher vapor pressure. Why? Because there's more molecules in the gas phase, therefore the pressure goes up. Okay, just like your tire. You go to the gas station, you put air in your tire. What are you doing? You're putting more molecules into your tire. Your tire pressure goes up. Okay, all right. That is vapor phase. The boiling point. Strong IMF interactions causes higher boiling points. Okay, again, these interactions are strong that the energy that we put into the system to get it to boil Quite a bit of energy is necessary to break those interactions apart, those IMF interactions. Again, because the IMF molecules are holding on to each other much stronger. And the same is true for a melting point. That is the temperature in which they go from a solid to a liquid. If there's strong IMF, we're going to have a higher melting point and a higher boiling point. Okay. Surface tension. That's surface molecules that hold on to each other strongly. So if we have a strong IMF interaction, again, we will have a high surface tension, simply because the molecules hold on to each other much stronger than those with lower IMF, depicted by this diagram here of A and B. A has a higher surface tension, therefore the IMF is stronger, therefore the A, you can see, beads up greater. It has a bigger bead than B does. B lies a little bit flat, again, because the molecules in B do not hold on to each other as strongly as the ones in A, okay, due to the IMF interactions. Viscosity, okay, we know that oil flows slowly, well, high density oil, because it has a high density, and things like vodka, for example, or water they flow much more rapid and have a low viscosity. And so strong IMF interactions results in higher viscosities. Again, for the same reasoning, the molecules are holding on to each other much greater, therefore resisting flow as readily as some molecules like water, an example, water versus honey, okay? All right, so let's compare two molecules. Now, what we can do here is just compare between two molecules. IMF, as I mentioned before, does not give us absolute values with respect to boiling point, surface tension, etc. Well, all we can do is compare A and B and determine who would have the greater boiling point, who would have the greater vapor pressure, etc. Okay, to do that, we first have to look at the molecule. And this is kind of ties it all together now, because now they're telling you in words, let's compare ammonia and fluorine. First, what IMFs do they have? Well, before we can do anything, we have to write the formula. Okay, so you might remember that formula of ammonia was NH3. We use ammonia multiple times. Also, we look at fluorine, and fluorine is one of the diatomic gases, okay? And so if it is Fl2. All right, so now we have the formula. So now we got to look and determine, okay, which interaction are we dealing with here? Well, right off the bat, fluorine is diatomic, which means it is nonpolar. So we need to determine polarity. Nitrogen is in group 5. Nitrogen is the central atom here. We use ammonia here in multiple times. And like I mentioned, with nitrogen being in the central atom, it will have a lone pair when we do the Lewis dot structures. So going back and refresh your memory on Lewis dot structures, we can determine that nitrogen has a lone pair on nitrogen, which tells you, boom, I got a polar molecule, okay, with 3 nitrogen-hydrogen bonds there. Very polar molecule. All right, so I'm comparing ammonia and fluorine. We look at the IMF interaction because we're dealing with hydrogen and nitrogen. Yes, there's a dipole, but because it's nitrogen and oxygen, we have hydrogen bridging force as far as the IMF interaction. Fluorine, which is nonpolar, the only force they have is London forces, okay? And so we're comparing the molecule with a very strong hydrogen bridging and very weak versus a molecule with very weak IMF, London forces. So first question is asked, who has the stronger IMF? Well, we just answered that. Hydrogen bridging has a stronger IMF, therefore ammonia has a stronger IMF force. Okay. So who would have the lower boiling point? Okay, now to answer that, you think about the force IMF interaction that they have. The one with the weaker IMF interaction would have the lower boiling point. And so London forces, remember the hierarchy of strength, London forces was the weakest, hydrogen bridging was the strongest, and with dipole somewhere in the middle. And so here, London forces compared to hydrogen bridging is the weaker force. Therefore, fluorine would have the lower boiling point. Okay. Which one is polar? Well, we know that because we needed to answer the force. And we know that fluorine is a nonpolar bond. So ammonia obviously is the polar molecule. Okay. Which has higher vapor pressure. Okay. Which has higher vapor pressure. Fluorine will have the higher vapor pressure because it has the weaker IMF interaction. And which, if there were liquids, and we're comparing two liquids here, okay, which would be less viscous, okay? Which would be less viscous, but that again will be fluorine because it has the weaker force. And then which would have the more surface tension, well, that causes the liquid molecules to bunch up together and to beat up. So the stronger forces would be involved there, and that's the hydrogen bridging forces. So ammonia would have the greater surface tension, okay? And so this is what we mean by a comparison, determining what intermolecular force is involved with that molecule. We can compare two different molecules, and from that, determine things like who has a higher IMF interaction, who has either lower or the greater boiling point, who has a lower or greater vapor pressure, who is greater or lower in viscosity, or who is greater or lower in surface tension, okay? Which allows us to make predictions. And so this kind of summarizes, it says there, as IMF forces, interactions increase, the viscosity increases, okay? Because the molecules are held onto each other much greater. The boiling point increases for the same reasoning. The molecules are holding on to each other much greater. Surface tension increases, same reasoning. However, same reasoning, the vapor pressure is much less because the molecules are holding on to each other much greater, less of them are being allowed to go into the vapor phase, okay? Now, in this is just one direction. It says as IMF increases, but that could have been worded as IMF decreases, and then all the answers would be the opposite of what is written there. So read the question carefully, okay? Water. Just going to talk briefly about water. It's very unique molecule, extremely unique. We know we went through the electrons Lewis dot structure. We have two bonding pairs. We have two non-bonding pairs. It is very, very polar. Water is extremely polar and will dissolve most of everything. You know, some of it very quickly, some of it may take years, but it will eventually dissolve it. What other thing? Because of the oxygen and hydrogen, has very strong hydrogen bridging forces between molecules, okay? And so it's very polar, has a very high IMF, low vapor pressure, unusually high boiling point, 100 degrees, and a freezing point or melting point of 0 degrees. Has high surface tension. And what's really unique about water, which is kind of unusual for water, for most compounds, is when it freezes, it literally expands. In fact, because of this expansion, the density of ice is much less than the density of liquid, and hence ice will float. Okay, kind of unusual. Unusual structures too. When the water molecules freeze up, to the far left you see some molecular crystal structures of ice, which is again unusual. But the one thing about it is a six-member ring. Nature has something about a six-member ring. Maybe it's just strength, but if you look around you, honeycombs and so forth, the structures of molecules, you always will find a six-member ring here. There's an image of a microscope. Supposedly, every snowflake is a little bit different as far as shape is concerned, which is pretty cool. Now, let's continue to talk. We're going to be talking about liquids in general, but I'm going to use water as an example. Okay, we have what's called a heating curve here. All right, so on the far left axis, on the axis going up and down, that is the y-axis, we have temperature, okay? And on the x-axis, that's the horizontal axis, coming down this direction, that's the amount of heat or energy we're putting into the system. So we can start in the far left corner where everything is at 0, 0. No heat energy, we're at 0 degrees, okay? At this point, if this was water, we would have a solid material denoted by the block here, which represents solid, being in a solid phase due to the low temperature. Now, as we heat it, okay, as we heat it, as we're going in this direction, as we add energy to the system, our temperature goes up, okay? And you can see here it goes up diagonally. Right? But in this area, we still remain a solid. What's happening here is we are heating it and we're breaking it up a little bit, okay? We're breaking up the interaction, the intermolecular forces. And then something interesting happens. We hit a particular temperature, which for ice or water would be 0 degrees. And we hit a first plateau, okay? And notice that as much heat as much energy as we give it, we're adding energy, the temperature remains the same. And what's happening here is on that plateau, we have a mixture of solid and liquid on that plateau. Let me change that color real quick so I distinguish the change. On that plateau there, notice straight across, the temperature remains the same, okay? All of the energy that you put into the system is being utilized by those molecules to break up the solid and create it and move it into the liquid phase, okay? When all of that energy has completed that process, and now you have all the liquid involved, the energy then for the temperature shoots up. Again, like we did in the beginning. And then this stage, in this particular area, okay, it's all liquid until we hit, guess what? Another plateau, okay, which this could be 100 degrees temperature, which could be water. So the first plateau is at 0 degrees, and the second plateau could be 100 degrees, okay? Now, at that plateau, there is a combination of the liquid and gas. And all the energy you put into the system, then nothing happens to the temperature, it stays up. The point being, if you're boiling water at the kitchen, once it boils and you're thinking that you're gonna make it boil more quicker or something by turning the heat up, you're wasting your energy. Okay, because all that energy that you put in, all that extra energy and put into the boiling water, the temperature will remain the same. You're not going to make it boil any quicker. So save your money. Once you got the boiling, the water is boiling to make spaghetti or whatever you're going to make, just lower the temperature enough to keep it maintained boiling, because no matter how much more energy you put into it, you're going to stay on that plateau until such time that all of that liquid gets converted to gas. And guess what? Your temperature then goes up again. Okay. And so you have two plateaus where the solid is being converted to liquid. And then the second plateau is where the liquid is being converted to gas. And no matter what you do with respect to energy, if you have a lot of water molecule in there, a lot of molecules or whatever you're working with, that plateau will remain constant until such time that you have converted all of one phase into the other. And then the temperature goes up. Okay. All right. And that basically summarizes everything I just mentioned. And this could be water. 0 degrees where it melts. It's all solid at 0 degrees. That's the melting point. At 0 degrees, you have a mixture of what's happening. The solid is going into liquid. Okay. And then when all the liquid is converted, the temperature shoots up to the next plateau, which again could be 100 degrees if this was water. And at that next plateau, no matter how much energy you put into the system, it will maintain that temperature until all of that liquid has been converted to gas. And then, yes, at that point, temperature shoots up. Okay. So that is our, and so during the phase change, the temperature remains constant. All of the energy that's put into the system at that plateau is being utilized to break up the IMF interactions. Okay. You are breaking up the IMF interactions. Please don't say you're breaking up the bonds. You're not breaking up the bonds. We see that quite a bit. You are breaking up the IMF interactions between molecules, which is allowing them to go into the next phase, from solid to liquid, liquid into gas. Okay. No bond breaking here. That being said, guess what, folks? They're done with chapter 14. And what I want to do is stop it here.